It's my pleasure to introduce Sándor Laki from the ALT University in Budapest. He's an assistant professor there, and he generally works in networking. And more recently, he has been focusing on novel features of data planes, such as programmability and flexible stateless resource sharing. And today, he's going to tell us about how programmable data planes can help revitalize industrial networks. Sándor, please go ahead.
Okay, thank you for the introduction. So in this presentation, I will talk about how programmable data planes can revitalize industrial networking. So what is the problem here? So there is an increasing demand from customers for more and more customized products. Personalized production is one of the key challenges in manufacturing, since it requires flexible production lines that can be reconfigured with ease in a cost-effective way. The softwareization trend has already started. This transformation seems to be a slow and sometimes painful process with lots of obstacles. So what is difficult? First of all, industrial applications have strict requirements. One, the continuous production cannot be interrupted. High security should be guaranteed to prevent unexpected damages and accidents. And finally, control loops have strict latency requirements. And what is more, industrial-grade devices were designed for long-term operation, 10 years or more, and updating the protocol is difficult or even impossible. Considering the high price, they cannot be replaced with smarter alternatives in short term. It's simply unrealistic. Finally, industrial protocols have emerged in the past decade. They are needed for ensuring the integrity between field devices and industrial controllers. Two widely used industrial protocols are Profinet and Ethercat, just to mention two examples. Profinet follows a traditional end-to-end communication pattern between I/O devices like sensors and actuators and industrial controllers like PLCs. They cyclically exchange their internal state with an update period of 1 millisecond to a few seconds. In contrast, Ethercat implements a daisy chain-like communication pattern where a master node periodically sends Ethercat frames over a chain of slaves that read and write the appropriate part of the same frame, just as you can see on this animation. So how can we increase flexibility in industrial environments? First of all, there is a trend on replacing hardware-based industrial controllers with software implementations running in a remote cloud or edge cloud sites. Though these solutions provide higher degree of reconfigurability and flexibility, the increased latency in the control loop or the transmission of large amount of data over the network, just think of images of video cams, may limit their practical application. Programmable data planes, however, can help in moving time-sensitive computations closer to the field devices and thus shortening the control loop of critical decisions. One example is FastReact that offloads event detection logic into P4 programmable data planes and trigger local actions if needed. FastReact reduces both response times and the amount of data to be transmitted over the network. The event detection logic is reconfigurable in runtime in contrast to previous proposals. Another trend aims at reducing the cost of recabling at industrial sites. Wired links are replaced by wireless ones using 5G radio, for example. Existing protocols like Profinet are very chatty. They were not designed for wireless environments. They periodically initiate state exchange messages, even if there is no change in the data to be transmitted. Considering a large number of field devices, the transmission of redundant data packed into tiny packets can lead to low spectrum efficiency and high energy consumption. Possible solution for this scenario is introduced in this paper. It assumes two P4 programmable devices at the two sides of the radio link and apply in-network filtering and caching to reduce the unnecessary data transmission over the radio link, while it also implements an active monitoring method for detecting link and device failures as fast as possible. One of the key advantages of this method is that it can be deployed seamlessly in existing networking environments without any modification in Profinet devices. As a conclusion, so the introduction of new network technologies in industrial networks is difficult. The support of industrial protocols poses many challenges. However, programmable data planes have the potential to enable incremental improvements in the network seamlessly without any modification in the field devices and protocols, like in the previous example. As a result, they can accelerate the deployment of new networking technologies in this rigid domain. We believe that programmable data planes can also provide practical solutions for recent challenges of industrial networking, like cloud robotics and real-time control in cloud and edge cloud, and can define new networking challenges as well, like pushing new P4 language elements needed for time-sensitive networking. And thank you for your attention.
Thank you, Sándor. This was very interesting. So I had a couple of questions. I think you mentioned that, this softwareization process has already kind of started, but it's going slow. So I was wondering, what is the status quo now? Do a lot of companies kind of move all the control software to the cloud, or they're just starting to do it? Like, what is the status quo?
As far as I know, there is a trend by the key players, let's say, in this industrial networking that started providing software solutions for the previous hardware approaches. Like these programmable logic controllers are key elements of industrial networks that controls the low-level processes. And most of the vendors who previously developed these hardware devices also sell or started selling software PLCs that run on edge computing, edge cloud infrastructures, or remote cloud infrastructures. Of course, what is important is the control loop. So in most of the cases, PLCs require closed loop and very low latency. Which of course can be guaranteed at edge computing infrastructures, but not in a remote cloud.
Right. Yeah, that makes sense. And does it do companies are kind of wanting to move also to the cloud, or has there been trends that they would just take the software, version, but still want to run things locally or have their own data center, or kind of those kind of things?
I think moving these computations to the cloud has many benefits. One of them that you don't have to maintain a computer at the industrial side. So the maintainability is much simpler, and maybe the let's say updating the given software PLCs or reprogramming them, reconfiguring them is much easier at a remote location or at a centralized location than locally at an industrial site.
Right. Yeah, that makes sense. And how does P4 fit into this whole picture? So I think you kind of mentioned about how we can offload some computation, but do you see it more as offloading some of the computation to P4 to kind of tighten the loop, or is there kind of part of the network protocol or the network itself that needs programmability and we can use P4 for that?
I think P4 is a tool which can be used for programming networking elements. However, the programmability itself has many benefits.
Right.
If you have programmable networking elements, you can also let's say, accelerate the deployment of technologies like replacing wired links to wireless ones without any modification in the existing protocol ecosystem in the industrial network. And I think it's it makes sense that we can exploit the benefits of new networking technologies. Industrial networks are mostly concentrate on low performance actually. So most of the industrial networks assumes 10 megabit per sec or 100 megabit per sec Ethernet, and And but nowadays, networking technologies are went further, let's say.
Right. But you think the programmability part can help in the industrial setting. So not necessarily maybe the high performance part, but the programmability part.
Yes, the programmability. I think high performance may also be important because in low speed networks, time sensitive networking was an important point because sending a packet takes a long time. And in this way, sometimes we have to stop sending an Ethernet frame and reschedule the packets, and we can send a more important packet instead of the previous one. But if we assume high-speed networks there, it may be not needed for anymore because of the speed of the network. So we can have guaranteed deliveries or delivery times without these very complex TSN mechanisms.
Right. Interesting. I think I have one last question, and that is, I think you mentioned that, we might need to change before or add something to it to kind of use it in this industrial setting. I was wondering if you could tell us a little bit more about that.
Yeah, the idea there was that TSN, I mean, time-sensitive networking is one of the key technologies used in industrial networks. And most of the devices, most of the industrial networking devices support TSN. And if we want to, let's say, integrate them with newer technologies like 5G connectivity at the industrial sites, then these new components should also support TSN. And currently, P4 is a bit, P4 focuses on traditional networking mostly. So just think of PSA architecture or Viva model or portable NIC architectures. And time-sensitive networking requires additional mechanisms, additional externs, let's say, or language elements. But I think that they can be implemented as a new TSN architecture model instead of a new components in the core language. So without modifying the core language.
Right. Great. Well, thank you so much. This was very interesting. Very interesting talk. Yeah.
Okay, thank you.